start. So how, I don't think anybody else is going to come. I just have 33 participants. That's fine. I guess we can start now. So last lectures we were discussing about how to improve any processor's performance, right? And we discussed that we can have a multi-processor configuration wherein we have multiple CPUs which can either work in an SIMD, MIST or MIMD architecture based upon number of instruction streams and data streams, how many of them are moving in parallel, just to improve the processor's performance in terms of speed, right? So with more speed, definitely we have more throughput and definitely better outputs. So in order to optimize with this procedure, we talked about multiprocessor configuration. Then in a multiprocessor configuration, memory again becomes a bottleneck. So if I have n CPUs which are operating in parallel with the in a given system, and then definitely I improve on the speed. But what about the memory? I can have two configurations of this memory. Either can I have a centralized memory, or I can have a shared memory kind of an architecture also. So I can have shared also, right? In a centralized memory, the architecture would look somewhat like I have drawn here. So we can have n CPUs and then a centralized major chunk or block of memory, and this includes all. So you talk about the main memory as well as the virtual memory. While when we talk about cache, every processor definitely would like to have its own cache. Are you all getting?
Yes, ma'am.
Okay. So when we talk about the centralized memory architecture, every processor has its own cache. Now see, everything, all the data, instructions, program, everything is stored here. And whenever any processor wants a certain part of that data or instructions, it caches the respective data into its own cache, and then it uses it according to its convenience. And locality is something which actually helps the processor to optimize its performance. So something which is being used again and again is cached into the respective CPU's cache, and then it can be used, right? Now this is a centralized memory architecture, and it looks very simple. So we have a major main chunk of memory, and then every processor has its own cache. But then, suppose a write operation takes place. Now, whatever is in the cache 1 for a data item X has been brought in from here, from the centralized memory, right? So the X item is now replaced with a new value by CPU 1, suppose. What about all other processors? Earlier, they all had the same copy of the data item X. Now, when CPU 1 has performed a write to the cache 1, either it is a write back cache or it is a write through cache, right? In both the cases, the processor writes the data item to the respective cache and to the main memory, maybe like later on or in the same go. So only your main memory and cache 1 are updated with the new value, right?
Yes, ma'am.
Okay. And this causes a problem called cache coherence amongst all other caches with the other processors. And we would always like to maintain coherence. So what do we mean by coherence?
Uniformity.
Yeah, parallelism, we can say, something which is I am speaking and coherently somebody else is also speaking in the same tone, in the same pitch, word to word same. So we say we are coherent in terms of, right now audio. Right. So when we take, say, in terms of data, a cache coherence problem would be something, maybe a data item which has been written to one of the caches and is not updated in all other ones. Well, we should have coherency maintained, right? So coherency is must for a multiprocessor architecture in order to, if we are talking about optimizing speed, and then if coherency is not there, everything is gone. So cache coherence is the major problem. The other architecture that we talk about is a shared memory architecture. right? And in a shared memory architecture, we would have, something um, like we will not have the centralized memory, right? And instead of these caches, each processor will have its own memory modules. So we'll have a respective, uh, you know, a main memory and a virtual memory for this one, this one, this one, this one, and so on. I hope it's not going fast. Anytime if you feel that I'm going fast, you can just stop me in between, okay? So we have see multiple memory modules with multiple processors, and in that case, we use specific networks called the butterfly. Oh, I did not teach beans, now. I had to finish this also. Oh, I forgot. Okay, so we have this shared memory architectures called the butterfly network and the beans network, wherein interconnections. I'll just stop share for a moment and open that slide to show you how. Three. Yeah, here it is. All right. So this is the respective beans network and the butterfly network that we did in our last classes. So in a shared memory architecture, we will have multiple processors having their own memories. So maybe processor 1, so processor 0 has a memory module 0, processor 1 has its own memory module 1, processor 2 has a memory module 2, 3 has 3, and so on up to 16th one, right? In such a scenario, each memory module is connected to every processor using these networks. So this is the significance of using these networks that we discussed last time. So if you all remember, we did the butterfly network last time. Beans was remaining. So what is your opinion? Should I teach beans first, or I should directly go to cache coherence? Please speak up. Yeah.
बीन्स करा दूँ मैं
हाँ, मेरे ख्याल
Beans.
से पहले बीन्स खत्म कर लें. आई फॉरगॉट दैट मैंने कराया नहीं. Acha. So, when we have a shared memory architecture wherein multiple processors have multiple memory modules, each is interconnected to every other memory module. So, every processor has an access to every memory module, and that is done either using a butterfly network or a beans network. Butterfly, we did last time, all the formulas, how the interconnections are done, we did everything. Let's move on to the beans one. Now, if you can just see um, between your butterfly and beans network, can you see some correlation? Just see the butterfly. This is your butterfly network, and this is your beans network. A beans network is two butterfly networks connected back to back, right? So if we just observe the butterfly network, if I divide the butterfly network into by a two, and then for the same configuration, and then if I connect two butterfly networks back to back, I'm able to achieve a beans network. Well, we do have formulas for calculating how the interconnections are done here also. So I've written also two back to back connected butterfly networks make a beans network, right? Okay, I'll just take the marker. Yes. Now, again, we need to find out how many rows and columns of 2x2 switches are required to make these interconnection. While you study data communication in the next semester, I guess, you will study about switches, routers. Some of you must have already studied about them in your industrial training. So, the 6 weeks training that you would have done in your second year, I guess. So maybe most of you would be aware of all these components, but still, if you're not, a 2x2 switch is usually used for telecommunication networks. It means that it has there is a communication device which has two inputs and two outputs, such that each input is connected to each output, right? So I drew it last time, if you all can recall. So something like this. Excuse me. So two inputs and two outputs. So we have straight connections also. So one will be connected to, so this is 1, 2, 3, 4. So one is connected to 3 also, one is connected to 4 also. 2 is connected to 3 also, 2 is connected to 4 also. So we do have straight connection as well as cross connection. It's a 2 cross 2 switch, right? Okay. Now, when we talk about this beans network, first of all, uh, we have to see how many processors have to be connected to how many memory modules. Right now, this shows an 8 cross 8 network, right? Definitely, excuse me, we need rows and columns of these interconnections. So the formula says that we have log base 2 of the number of processors and memory modules that we want to connect. One more thing, we always have this as a matrix. So if I'm saying 8 processors to 4 memory modules, I will have to use an 8 cross 8 network. I can leave some outputs vacant, but I will have to use a matrix which is 8 cross 8, right? Now, 8 processors and 8 memory modules right now. This means log base 2 of 8 is I've written wrong formula. This is n by 2. Sorry. Log base 2 comes for the column. So n by 2 rows, that gives me 8 by 2, which is 4 rows, right? Okay. So I have 4 rows for processors and 4 rows for memory modules. I'll keep drawing it side by side. So this is row 0. I have row 1, 2, 3, and this makes 4, right? Similarly, we'll have the downwards also. So 4 rows for processors and 4 for memory modules. Then the columns I have to be found out using log base 2 of n. So again, now when I talk about the columns, 1, 2, 3, right? So log base 2 of 8 becomes 3 right now. 1, 2, and 3. One extra, so log base 2 of n plus 1 is always required because 1 is a back to back connection. Are you getting? See, when we talk about the beans network, it is a little different from the butterfly network. For a butterfly network, we directly had this kind of a scenario. Here we directly had this kind of a scenario wherein for 16 memory modules and 16 processors, we just required n by 2 rows and log base 2 of n as the number of columns. But here, if we talk about the beans network, it is a back to back connected butterfly network. This means if I have taken 3 columns, one extra column is required for a inversion connection also. उसको U turn करके वापस भी लेकर आना है. So one extra column for that. Okay, though I have not written it, but it is required. Yeah. At each interconnection, we use a 2 cross 2 switch. Now, if you just realize the last column has 2 inputs, but the outputs are left unused because these are back to back connected. So these are brought back inside. Okay. Now, at each interconnection, we have a 2 cross 2 switch. So one here, and one here. And the formula for the connection remains the same. So for all the downward connection, we have row plus 2 raised to the power column. And for all the upwards connections, we have row minus 2 raised to the power column. So if you will just realize, just if you will just realize, we get the same connections as we did last time. So if you want, I can calculate for you also. So this one comes here, this one goes here, this one goes here, this one goes here. Let's see the last one. Let's see the last one. This is row 0. बच्चे समझ आ रहा है? Are you all getting?
Yes, ma'am.
Row 0 and it is column 0, 1, 2. कॉलम 2। ठीक है, लास्ट टाइम हमने ये दो कर दिए थे, इसलिए इस बार मैंने ये नहीं किए। Excuse me. Okay, now let us see how these four are connected to the lower four ones. Okay, now this is row 0 column 2. The formula says row plus 2 raised to the power column for the case of downwards connection and minus for the case of upwards connection. So the first one is row 0 and column 2. So this becomes 0 plus 2 raised to the power 2 gives me
4.
4. So row number 4 is the cross connection now. So row 4, 0, 1, 2, 3, and this is the fourth one. So this comes here. Right? Let's see the next one. This is row 1, column 2. So 1 plus 2 raised to the power 2 makes row 5. ठीक है ना, समझ आ रहा है?
Yes, ma'am.
Next one, row 1 हो गया 2. Row 2 and column is again 2. So 2 plus 2 raised to the power 2 makes row number 6. This one. And finally, we have row 3 and column 2 again. So 3 plus 2 raised to the power 2, 4 makes row 7. Right? Now, these 2 cross 2 switches are not utilizing their full potential. This is why I did not write log base 2 of n plus 1 over here. So this plus 1 actually is an not fully utilized kind of a switch. While if I just talk about the remaining connections, which from here have to be made back to the memory modules. So if I just realize this one now, this is row 0 and column 3. Now downwards connection we have to make because there is no upward connection which is possible. If I just talk about the downwards connection, this is row 0 and column 3. So become 0 plus 2 raised to the power 3 is minus, sorry, I should use the minus one. Downwards connection, it will be row minus 2 raised to the power column. This becomes, currently, it becomes row is 0 and minus 2 to the power. Oh, can you just hold on for a minute? I have, there's a power cut. I'll just switch on to the UPS. Just a minute. Huh? All right. Yes. So it is row 0 minus 2 raised to the power. Yeah. What is the column number? It is 3. Are you getting?
Yes, ma'am.
Yeah. So this becomes minus 8, right? And if we talk about right now, yeah, this will not hold. And row 1, इसका बच्चे formula फिर मैं next time बताऊंगी Beans network का. This does not hold. It will hold for all other cases, but not for the last one. And that is why we have not used it in the formula. प्लस ही आएगा, माइनस नहीं आएगा. This becomes 8. Chalo, I'll let you know about this one in the next class. Okay. So all the till here where we have calculated log base 2 of n, till here all the formulas hold correct, but not for the last one. And for the last one, I'll let you know how it has to be connected. So if I just calculate these ones, they will all be fine. इवन दिस विल बी फाइन, दिस विल ऑल्सो बी फाइन, ये भी ठीक चलेगा, यहाँ तक सब ठीक चलेंगे। इसके बाद वाले में थोड़ी सी प्रॉब्लम है।
उसमें मैम हम टोटल में से माइनस नहीं कर सकते?
एक्चुअली फॉर्मूला से डायरेक्ट आना चाहिए, टोटल में से माइनस, वो फिर ना इट गिव्स मी समथिंग विच इज ऑड फ्रॉम द यूजुअल। इफ आई
हाँ,
जस्ट
वो
से दिस
अगर
वन,
मेमोरी मॉड्यूल से ऊपर कनेक्शन लगा दे जो
हाँ
हमने।
वही दैट्स व्हाट आई वाज अबाउट टू से, दैट इफ वी ट्राई एंड कनेक्ट फ्रॉम हियर, is the drop on, yeah, if we start trying connecting from here, this means this is row number 0 1 2 3 4, row 4 and column 2. So हाँ अब ठीक आएगा, I guess now it should be fine. So this should be row 4 minus 2 raised to the power, column number is 0 1 2 2. हाँ अब ठीक आ रहा है, yes. So this gives me row 0. Yeah. So I guess I started from the wrong place. That's why I was not able to connect. We have to start from only from the till this one, till where we have calculated. So till column number 3 only we have to start, right? And this gives me row 0. If I calculate for the next one, this is 1. So this is row 5 minus 2 raised to the power 2. 4 gives me row 1, right? Row 6 minus 4 gives me 2, row 2, and row 7 minus 4 gives me row 3. So since I just like to impress upon this one, since these switches are not fully utilized to their potential, we will not apply any formulas for their interconnections, right? We would always like to talk about the memory modules or the processor modules switches only, till where they are fully utilized. तो यहीं से connections draw करने हैं या तो यहाँ से या फिर यहाँ से, ऊपर से नहीं खींचना है बच्चे, ठीक है? I hope it's clear everyone.
Yes, ma'am.
All right, let's move on. So this was your beans network and the butterfly network. So let's move back to cache coherence from where we had left. Yeah. Now, so when we talk about these multiprocessor architectures, either can we have a shared memory module, a multiprocessor architecture wherein we have a centralized memory which is shared by all the processors, or we can have every processor having its own memory module which is shared by all other processors using either a beans network or a butterfly network, right? So having done with the beans and the butterfly, next job is to talk about cache coherence that has to be maintained amongst all the caches of a multiprocessor architecture. So we just saw how the architecture would look like, and every processor will have its own cache and there will be a central memory which will be shared by everyone. Now, um, so the multiprocess architecture with multiple caches supports the caching of both shared and private data. So every processor can have its own private data as well, and there can be a shared data which has to be shared by all other processors. Can be both, the configurations are possible. A private data is used by a single processor while a shared data is used by multiple processors, essentially providing communication amongst processors through reads and writes of the shared data. So I don't need to explain all this. When a private item is cached, its location is migrated to the cache, reducing the average access time as well as the memory bandwidth which is required. While when a shared data is cached, the shared value may be replicated in, see, this is a very, very important point. I would like to impress upon this. Yeah. When a shared item is cached, the value may be replicated in multiple caches, in addition to the reduction in access latency and required memory bandwidth. So now, whenever we talk about a shared item, excuse me. Okay. So whenever we talk about a shared item, it has to be available in all other caches as well. And that causes a cache coherence issue. which is very, very important to be addressed by a multiprocessor architecture, right? Just a minute. Huh. Okay. Yes. Now, what is actually a cache coherence problem? We can explain with the help of this diagram, right? So the figure below illustrates the problem and shows how two different processors can have two different values for the same location, and this is referred to as the cache coherence problem. When any processor writes to a shared variable in its own cache, all other caches must contain the new copy. If they have the old copy, that is called as cache coherence. Let's see what happens. So at time t0, so we have a location x, memory location, which is x, right? Its contents are maintained at a value which is 1. Now, at time t equal to 0, we have two CPUs in the architecture. So we have CPU A and we have CPU B. At time t equal to 0, nobody wants an access for it, so it's fine, no problem. At time t equal to 1, CPU A wants a read for x. So it sends a control signal for read of x to the memory. And it reads a value of x equal to 1 from the main memory since its own cache was empty. Right? पहले इंस्टेंट पे तो अपनी कैश एम्प्टी होगी उसकी. Are you all getting? आ रहा है, समझ आ रहा है?
Yes,
थोड़ा
ma'am.
okay. So um, yes, so in the first instant, cache for CPU A is empty. There is a read miss. It goes to the main memory. From the main memory, it gets the value 1 and caches x is equal to 1 in its private own cache, right? Then at t equal to 2, CPU A's cache already has x equal to 1. Then CPU B, it also wants to read x, and it sends a read signal on the control bus for the memory. Obviously the address should first of all go to its own cache. It goes to its cache, it's empty, it's fine. It incurs a read miss, a cache read miss, and definitely the address goes to the main memory now. And definitely x was 1 there, it gets x equal to 1 and caches x equal to 1 in its own cache. So now at time t equal to 2, CPU A's cache also has 1 and CPU B's cache also has x equal to 1. Right? At time t equal to 3, CPU A writes a new value of x equal to 0 into its own cache. Obviously now it wants to perform a write operation for x. So it stores a 0 into the memory. And whenever the address goes to the memory, it always goes in hierarchical order, right? So it first of all goes to the um, cache of CPU A. And cache of CPU A has a location X. It is there. So what happens? It modifies X equal to 0, and depending upon whether it is a write back or a write through cache, it modifies the value in the main memory also. Getting?
Yes, ma'am.
Okay, okay, good.
Yes, ma'am.
Okay. Now, if we just see this scenario wherein we just have two processors and two caches respectively with the two processors and a main memory, the main memory contains the updated version of X, and the respective CPU also contains the updated version of X. But what about CPU B? It still reads X equal to 1, and there is no coherence between the value of X, which should be there between CPU A, CPU B, and the main memory. So this is actually the cache coherence problem, and we need to overcome it. यहाँ तक क्लियर है तो फिर मैं आगे बढ़ जाती हूँ.
Yes, ma'am.
Okay.
Yes, ma'am.
Yes.
Clear, ma'am.
Okay. Now, so when do we say any system is coherent? So first of all, see, if a read by a processor P to a location X that follows by a write by P to X with no writes of X by any other processor, between the write and the read by P always returns the value which is written by P. So this is what it actually means. I'll just draw it for you. So this is a processor P, right? And this is the shared bus. In a multiprocessor architecture, we always have a shared bus. So this is the shared bus, and and then this is the main memory. Oh, this is the main memory. Right, and location X. Okay, so we have a location X here and a location X here, and we have one more processor, let's say. So we have one more processor. P की जगह N ले लेते हैं, ठीक है? Now it says that a read by processor P to a location X, right? इसने इस लोकेशन को रीड किया एंड देन फॉलोड बाय राइट बाय P to X. तो अब इसने इसको अपडेट कर दिया with no rights of X by any other processor. इसने उसको टच भी नहीं किया, right? And then with no rights of X by any other processor, occurring between write and read by P always returns the value which is written by P. Now, whatever value this has been written to, the updated value should be returned by N when it wants to read X, and by the main memory also. So this is what cache coherence says. Another definition for cache coherence is that a read by a processor to a location X that follows by a write by another processor to the X returns the written value if the read and write are sufficiently separated with no other writes to X occur between the two accesses. So again, the same thing that if P is reading a new a value of X and then N is writing to X, right? Then if there is no other read or write between these two accesses, the latest updated value should be returned whenever X is read by any other processor. And then one more thing it says that writes to the same location are always serialized. That is, two writes to the same location by any processors are seen in the same order by any other processor. Now, suppose we would have had one more processor here in the system. If you're getting, are you all getting what I'm trying to say?
Ma'am, what is N? It's another processor.
Yeah, N is another processor. P, N, and Q. These are three processors right now. MMX is the main memory module, and there is a location which is X in the main memory, and then P writes to it, right? Now, what it says is that whenever P updates the value of X, and then if any other processor wants to read X, it should always get the updated value. This is one definition of coherence. The other says that if P has read X, not written, and then N has written X, then maybe next time when P wants to read X, it should also return the most updated value. Are you getting? It's like, three of us, maybe me, you, and there is some other student. We are sitting in a group and we are playing a game called Chinese Whisper, if you all remember, if you would have played the game in your childhood days. So every time the three people in the group, they say a new word, that new word should be known to all other two people in the group. That's it. Okay? So if there is a location X in the main memory and that has been cached by processor P, right? And P writes a value to this X, then N, Q, or main memory, any of the accesses should return the most latest value which has been written into the X. Secondly, if P has just read X and N writes to X now. So if N is writing, N is updating the value. So from 0 it becomes 1. Now if P reads it again, it should get the most latest value. Getting?
Yes, ma'am.
Right. And lastly, it says that two writes, maybe two or more than two writes to the same location. Say P has written to X and then N has also written to X. And then when Q wants to read, now Q wants to read the value of X. What should happen? Should it skip values or it should see the values in the same order? Okay. So it says that writes to the same location must be serialized. That is, two writes to the same location by two processors should be seen in the same order by all other processors. For example, if the values 1 and 2 are written to the location X, say X was updated as 1 by P and then 2 by N, right? Then processors can, yeah, so then processors can never read the value of the location 2 and then later read it as 1. So if it reads it after N has written, it should always get the updated value. Getting?
Yes, ma'am.
Yeah. So this is what cache coherence actually talks about. Not just the diagram that we discussed right now. So that diagram was just to explain you what is cache coherence problem, but actually coherence talks about all reads and all writes, right? So this was just an example to tell you what is coherence problem and how it takes place. Uh, and then when we talk about coherence, it actually takes into account of all reads and writes. So maybe there is one processor that writes a location and then all other processors want to read the updated value, they should always get the updated one, right? And then if a processor just reads a value and some other processor writes an updated value for the same location, the next read should give it the updated value. Coherence होगी तभी मिलेगी ना उसको. And thirdly, when we are writing, so maybe processor P and Q, there were three processors in the architecture right now. All three are writing to the location X after one, after other. So the writes to the same location should also be serialized. It should not take place, in the same go, all three processors want to write X. No, that should also not happen. And secondly, if they are written in a serial order, all other processors should read the value also in a serial order. ऐसा नहीं होना चाहिए कि 1 के बाद 2 लिखा, उसके बाद 3 लिखा और Q ने एक्सेस किया तो उसको सीधा 3 मिले. नहीं, जब 1 लिखा तो सबकी वैल्यू 1 होनी चाहिए X की. जब 2 लिखा तो बाकी सब प्रोसेसर्स के कैश में X की वैल्यू 2 होनी चाहिए. और जब 3 लिखा तो बाकी सब प्रोसेसर्स के कैश में वैल्यू 3 होनी चाहिए. आई होप इट्स क्लियर नाउ.
Yes, ma'am.
Okay, good. Yes. Now, so in order to just a minute, huh?
Ma'am, time.
2 मिनट रह गए हैं.
हाँ जी बच्चे, yeah somebody 10:30. तो I started 10 minutes late, no? अब बच्चे देखो
We
मुझे
have other class. Okay.
you have it at 11:20 if I am not wrong. Okay, there is no problem. I can conduct an extra class on Monday or Tuesday maybe if you want me to finish off with this topic. So tell me right now if you're coming for the next class. There's no problem. You can tell me frankly. Speak up. Am I audible? Ria?
Yes, ma'am.
मुझे बताओ फिर नेक्स्ट क्लास में Are you people coming? Because I have to finish off with this topic. Quite a lot bit left. पूरा
Yes,
बता
ma'am, you can take the extra lecture.
Yeah, I'll take one extra lecture because I missed one lecture, if you all remember. So one extra lecture should be enough, I guess. उससे ज़्यादा ज़रूरत नहीं पड़ेगी. चलो, I'll wind up right now. Okay, बच्चे. Start your class.